We are from Group 4 Peter Lab section. We had to design and implement an FPGA-based 4-digit combination lock. This lock uses switches to enter digits from 0 to 9, one digit at a time. This lock continuously compares the entered 4-digit sequence with a pre-programmed golden code which is stored in a register.
Implemented our various modules here, starting with the tick generator. This is our clock divider. The debounce enter is a module which cleans the noisy push button signal and outputs a 1 cycle pulse on a valid press. The sync switches synchronizes the switch inputs. The shift reg collects the 4 entered digits. The FSM lock controls the entire lock procedure. The lock VIO provides the VIO interface, and the top connects all the modules together and links them to the set board. This is our current status of our ILA waveforms, and using the VIO we can input our golden code. We are using 1, 2, 3, 4 here, and then using this we can write it onto our waveform. We can see that it has been reflected in the waveform.
This case is to enter the correct code, due to which the lock will stay in the unlock position for 2 seconds. Our next test case is to enter the wrong code, due to which it will be in the lockout state for 5 seconds. The next test case is if the lock is either in the unlock or the lockout state, it doesn't take in new inputs. This case is to show that if reset is pressed in any instant, it clears all the inputs.
The FSM state 0 indicates the idle state. FSM state 1 indicates the right state, which is when we input the 4-digit code for the lock. FSM state 3 indicates that it's an unlock stage, and FSM state 4 indicates the lockout stage. This is the schematic after the RTL analysis. Schematic post-synthesis, schematic post-implementation, the hardware utilization report, the timing analysis, and finally the power analysis.
I'll be explaining how all our different modules work together to make our digital combination lock work. The first thing that happens is the reset path. When the Z board powers up, or when we press button 1, the reset synchronizer makes sure every module starts in a clean and predictable state. All internal registers, which are the shift register, the digit counter, the FSM, and the timers, are reset to 0. This puts the entire system in the idle state, waiting for the user to enter digits. From here, the 100 MHz onboard clock drives the whole design. We feed this clock into the tick generator, which converts it into a 1 millisecond pulse. That millisecond pulse becomes our timing backbone. Debouncing, timers, and parts of the FSM all rely on that steady 1 millisecond pulse. Now, when the user presses button 0 to enter a digit, the signal is noisy, so the debounce module steps in. It checks the button stability over 20 milliseconds, and once it's sure the press is real, it produces a clean 1 cycle pulse called enter pulse. Exactly when that pulse happens, the sync switches module captures the value present on the 4-bit array called SW. This becomes our digit. It also generates a digit valid pulse, which tells the rest of the system that a new digit is ready. Every time digit valid goes high, the shift register shifts left and appends the new nibble. After 4 entries, the shift register holds all 4 digits the user typed in, and the digit counter reaches 4. At this moment, the FSM switches from input state to check state. In the check state, we compare the entered code with the golden code. The golden code is normally set to the virtual I/O interface, and we only allow updates when we are in the idle state to prevent accidental overrides. If all 4 nibbles match, the FSM moves onto the unlock state. It starts the unlock timer, which keeps the unlocked LED on for the required 2 seconds, then clears the shift register and returns to idle. If the code doesn't match, the FSM goes into the lockout state. The lockout timer runs for 5 seconds, during which the lockout LED stays on, and during this time, the system ignores button presses and virtual input output rewrites. Once the timer completes, we clear the shift register and return to idle state again. So overall, each part of the design plays one specific role. The clock and tick generator establish timing. The debounce and switch synchronizer clean up inputs. The shift register builds the 4-digit code. The FSM decides what to do with it. The timers enforce unlock and lockout durations. And the virtual input output module gives us a flexible way to get the golden code, to set the golden code without touching the hardware. And that's the full flow from power on through digit entry, comparison, timing, and output, all running in hardware on the FPGA.